So today we will learn how to deal, calculate, propagate, generate, analyze errors in your data. Two main rules. First, every time you do an experiment, you generate errors. For example, when you measure volumes, when you measure mass, when you titrate and you get the difference in the burette reading, you generate errors. That's just because we're not sure how the instrument will measure the quantity, right? That's the first rule. Second, every time you calculate now, so when you multiply, add, subtract, divide data that you have generated, you propagate errors. Okay, I wanted to make a song out of it. When you experiment, you generate errors. When you calculate, you propagate errors. Clear? When you experiment, you generate or you make errors. When you calculate, those errors add up. It's propagated. All right, so let's understand her experiment here. A background of her experiment. She's measuring the specific heat capacity of different cooking oils. So this is how I grade it. Investigation of specific heat capacity of different cooking oils. Then I look at the very final table because the final table should answer the question. So we look at her final table. Final table or final graph. There. Did she answer her research question? Yes, she did. So which oil has the highest specific heat capacity? Olive oil. Therefore, she said olive oil will be the most ideal oil to use when you're cooking. Why? Because it absorbs a lot of heat per gram per mole, right? Um, anyway, if you look at her final graph, there, she's also able to show it to you. It's olive oil, the highest specific heat capacity. Now, let's look at what are the errors though when she was experimenting, what are the errors she generated, and what are the errors she propagated when she did her calculation. So let's look at table 1. Okay. So, table 4, not 1, sorry. Table 4 here, this is specific heat capacity of canola oil. As you can see, every time she measured the temperature, she generated an error. So that's what you can see here, plus minus 0.1. She measured the temperature again, 0.1, right? Then she measured the change in temperature. She propagated an error. That's propagation because she calculated, right? Plus minus 0.2 now. You understand where we are so far? So her specific heat capacity. Why do we need change in temperature? Because what formula do you think she's using here? MCAT. So MCAT, and if you're given the mass, you're given the temperature change, then you can solve for the, and then if you have Q, then you can solve for the specific heat capacity. Okay, let's hold up for a minute. Do you know how she measured this? Why do I need the temperature change of water? Okay. Like this formula right here. So let me explain what she did here. She put the oil here. So this is oil, and it was surrounded by water. Okay. She did not heat this up directly. What she did was she heated this up first. Okay? Because the heat of this can be the Q of this. This is what I'm talking about. So water, Q MC delta T. She knows the mass of the water or the volume. She knows the specific heat. She calculated the delta T, right? If she knows that, then she knows Q of water. But the Q of water is the same Q of oil, right? because the heat just transfers to the oil. This is made up of metal, so that the heat change of this transfers here. So if we calculate for C, so you have the Q, right? You know the mass of the oil. She also measured the temperature change of the oil. That's why if you look at her table right here, she has the temperature changes of the oil, temperature changes of the water. You understand? So you can calculate for the C there. Okay. Now, let's look at error generated. You already know the error generated right there. Now let's look at error propagated. So first of all, she calculated the specific heat capacity of oil. So that's 3.98. Now what are the errors here? Errors. Scroll down. Please ask me questions if you can't follow the calculation. Okay. Where did this 3.99% come from? Mass of water, 0.5. Sorry. For the mass of water, the uncertainty is 0.5. I think that her volume is 100, if I'm not mistaken. That's why 0.5 divided by 100 times 100, that's the percent uncertainty of the mass here, right here. Maybe this is not clear. If I were you, you're gonna put the label what this is right here. Uncertainty of the mass of water. Questions? You understand? Next, do I have uncertainty for C? No, it's a constant.
Yeah.
Okay. Do we have uncertainty for temperature? Yes. You said it was 0.2, right? Right here, 0.2. So 0.2 divided by the temperature change is 12 times 100. So you get the percent uncertainty of that. And then again, percent uncertainty of mass of oil and percent uncertainty of the temperature of water. So you're calculating C now, but each variable there, this one, this one. So this one, have their own uncertainties. So you get their percent uncertainty and you add them all up. That's where 3.99 came from. Question? So we're clear. So this 3.99 right here, came from adding all of the individual percent uncertainties. So you do that for trial 1, trial 2, trial 3, trial 4, right? That's the 4.01, 3.95, 3.78. So your overall, where did this 0.154 come from?
Average.
Average. So add this divided by 4. Which is actually a percent. Miss, what is that? That's absolute uncertainty. So the percent, she converted it into absolute uncertainty. Why, Miss? Because she wants to compare it with a variance. I'll teach you what that is. But anyway, in your calculator, can you try to add 3.99, 4.01, 3.95, 3.73? Divide by 4. 3.92%. 3.92? Now, what is 3.92% of 3.92? Did you calculate this, right?
3.92 times 0.09.
0 point? Okay, so that's the absolute uncertainty here, 0.154. If you want, you can actually put 3.92 plus minus 3.92% or plus minus absolute uncertainty, that's fine. But why did she want to show it as an absolute uncertainty, not a percent? because there's what we call variance. Let me explain what variance is. What is variance in math?
Like how far it is
From the mean.
from the mean.
Okay. So if we calculate the variance, the formula for the variance is, please remember, maximum minus minimum divided by 2 square root of number of trials. Write it somewhere or in your brain, try to remember. Maximum minus minimum divided by 2 square root of your total number of trials. So her variance is 4.28, that's the highest, specific heat capacity, minus 3.65 divided by 2 square root of 4 is 0.158. Miss, why are we doing that? Now, variance is, in theory, in mathematical theory, this value is the accepted variance, or you can differ by plus minus 0.158. You can, it's acceptable. In math, so you have she has 4 trials, right? All of her 4 trials, using mathematical theory, can generate this error. It's acceptable. Meaning, if you compare your variance with her calculated propagated error, so you can see the acceptable error is 0.158. We got it from our variance. That's greater than your calculated average uncertainty, which is 0.154. Meaning, you're within the window of making a mistake. Do you understand? I hope you do. Some teachers don't understand this. In my workshop, we were talking about variance, and for them, they didn't use variance. They just interpreted the uncertainty. But it's good to interpret your uncertainty basing it on what is acceptable in the variance. Now, maybe many of your calculations will constitute random errors, I hope. If this variance is less than your average uncertainty, you have so many errors. That's not acceptable. So it may not just be a random error, it may be a systematic error. There's something's wrong with your equipment, maybe. You understand? That's the purpose of the variance. As you can see here, after she calculated the variance, she put an interpretation. Thus, this experiment is made up of random errors. May institutes. I don't like that. This experiment generated random errors. Clear? That's for canola. Do we have questions so far? Okay, do we understand how we're propagating errors? So your final propagated error right here, you said is 3.92% or 0.154. We converted it into absolute uncertainty because we want to compare it with our measured variance. Clear, clear, clear? I hope this is clear. So I don't want to reteach this when you're analyzing your errors. I'm going to say, oh, add that. Oh, where's your percent uncertainty? What's the total percent uncertainty? Now compare it with what? I will just keep.
Basically, when you're adding values, you add the absolute uncertainty.
Adding?
Yeah.
A rule before. Whenever you multiply or divide, you add the percent uncertainty. Whenever you add or subtract, you add the absolute. Like this one, temperature. Like you just subtracted, right? So you just added 0.1, 0.1. It became 0.2. For specific heat capacity, you multiplied and divided. So instead of just adding the absolute uncertainty, you calculated the percent uncertainty first and added them all up. That gave you 3.99. What's the purpose of the variance again?
To see if your experience
Difference between your experiment and
is accepted.
accepted in theory. It's accepted for you to get that error. So I hope you will just say random here. Okay. So pretend you understand how she did this for the rest of the oil. Okay. By the way, don't think about your experiment yet. Just think of this. Then try to understand how we're treating the errors. Now, so you'll expect that she will have a final table of all the specific heat capacity of the different oils. So if you look at table, okay, table 9 here, table 9. So canola, we just looked at that. That's 3.92. Are you in table 9? So 0.154, right? We've looked at where that came from. So she listed everything for all of her oils. And as you can see, this is absolute uncertainty. She has another column to express percent uncertainty. 3.9, she said 3.92 earlier. Maybe she rounded it because she has 3.93 here. Okay, so we have the specific heat capacity, absolute uncertainty. Why express it as a percent again here? Okay, listen again. This is because she tried to account for other uncertainties in her experiment. Remember, this 3.93 came from her formula, like uncertainty of this, and this. So she added it all up. It it was equal to 3.92, 3.93, you said, right here. There may be other errors, such as, so look at the next table, other percent uncertainties, such as the voltage. Now, voltage is not in her equation, right? So earlier, when she was doing MCAT equals MCAT, she didn't really put voltage. It's not in the formula. But it was in her procedure. So she has to add uncertainty from the voltage and the ampere. Those are the voltage generator that she connected here. Did she have to account for time? Yes. Because you're uncertain also when you record your data, you might be plus minus, I don't know, 1 second away from when you are supposed to put it. She also added volume of the sample of the oil that she put here. It's not in the MCAT formula, so she added that. Even the volume of water. Wait, I have circles here. What did I put? Oh, great, the source of error. Volume of water. The sample of water here. So, this is what I'm trying to say. In her calculation, it was just supposed to be 3.93. But if you consider everything that you did, every single thing that you did can generate errors too. So you add them here. This one, voltage, ampere, time, volume, maybe volume. And 3.93 was her original percent uncertainty from calculation plus all the other percent uncertainties equals, now it's 5.71. Are you still with me? So she's adding up everything, every possible source of error. Now it's 5.71. Now in this table, you can actually comment. She forgot to comment. Comment on the variable that you measure that produced the most uncertainty. In her case, this one, 0.7, 0.5%. That's really big compared to 0.1 in time, 0.14, 0.3. So this, I said here, comment that this is the greatest source of your error. Okay. So her very final table is now here, 3.92. Remember, this was supposed to be 3.93. Now it's 5.71. So instead of 0.154, now it's 0.224. Okay. This is now analysis. Earlier, we said variance 158 is greater than 0.154, right? So we said it's random. But look now. It's now less than. Please think with me. It's now less than your absolute uncertainty. So what does it mean? Not only do you have random errors, you may have systematic errors. So this experiment also has systematic errors, she said. Earlier, she said just random. But if you look at the whole procedure, the calculated variance is now smaller than your added uncertainty. All of your errors were bigger than what's allowed. So there's something wrong with the system. That's fine. You may have systematic error. You know why? This is a lab. This is a high school lab. We don't have the perfect equipment here when you're gathering your data. In her case, calorimetry, if you remember, this generates a lot of heat loss to the environment. That's a very big systematic error for her. She was trying to wrap this in styrofoam, like icebox. She had to create several equipment, by the way, to make sure that it's insulated. But in a perfect world, we can't really account for the total amount of heat here. There's going to be some heat losses here. This is metal too. Heat can be absorbed by the metal itself, so some heat can go to the metal, can't be 100% efficiently transferred to the oil, right? So she said there are systematic errors here. Now, let's just look at her discussion of the errors. By the way, make sure you can, in bio, I taught you how to put error bars, right? So your error bars, in bio, it's okay if you don't know. In bio, error bars are based on what? The calculated standard deviation. In chemistry, the error bars, this one, is based on your final calculation of absolute uncertainty right here. Notice there's no standard deviation in chem. We don't have standard deviation in chemistry. We just have propagation of uncertainties. So this 0.0224, 0.211, 0.254, 0.252, 0.229, that's this error bars right here. Okay? Hmm? Constant and individually plot those error bars. Okay. So, look at her comment here from the graph. Olive oil has the highest specific heat capacity. Corn oil has the lowest. Just like in biology, put short descriptions after every, not just a final, after every table and graph. And then error bars, again, are calculated from average uncertainties. It's found in table 11. It's easy to follow her discussion here. And then she also commented that the canola oil has the biggest uncertainty, meaning you're most no, hold on. You're most unsure of your data for canola oil. It has the biggest error bar, so probably you will need more trials. You're not precise. The bigger the error bar, the more imprecise your data is. The smaller it is, the more precise. Okay. So discussion here. So she answered her research question. She said that it was canola oil, and then she discussed her data. So these are her numbers. As you can see, there are numbers here. 2. Okay, the variance is smaller than the average uncertainty, indicating possible systematic errors. From the experiment, this may be the weakness of the insulator. So she thought about which one may have given me a systematic error. Remember what systematic error is? There's something wrong with the equipment or the method. For example, if you always look at instead of eye level, you always look at like this. So even if you repeat it 1,000 times, but your method of looking at the water level is wrong, there's something wrong with the procedure. It's always going to be systematic error. So she said it may be the insulator. So no matter how many times she repeats this 1,000 times, the heat change it's always lower than what she wants it to be. Always lower. So the insulator for the oil was different in terms of styrofoam, not fully covering the calorimeter. Thus, there are heat loss to the environment, which is an essential, important aspect here when you calculate specific heat. So I said good analysis. And then her conclusion, she backed it up with science. So why olive oil? Why olive oil has the highest amount of heat per gram? So she has some discussions, somebody to back her up. Thus, okay, evaluation. She said errors are mostly systematic, but it also has random errors. So every time you have systematic errors, there's always random errors. But every time you have random errors, you don't necessarily have systematic errors. There's random errors are given. Okay, random errors are given and they're allowable. That's why we calculated the variance. So she mentioned the rest of the or errors here. As you can see, when you discuss your errors, you have to categorize them whether it's systematic or random. Okay, it's random here. Okay. Any question? Every time you experiment, you measure something, you generate errors. Every time you calculate, you propagate errors. No questions? Okay, those who are done, go ahead and try to look at your tables. I can help you with error propagation. Probably in the pencil and paper first. Then I can say I can tell you like, oh, where's the error here? Where's the error here? Did you add this? Add that, like that. Then you can continue with your experiment.